At this point, I'd like to formally welcome Dr. Tanzi to University of Rhode Island. He's an eminent biomedical research scientist and the Kennedy Professor of Neurology at Harvard University. He's the director of the Genetics and Aging Research Unit at Mass General Hospital, where he investigates the genetic causes of Alzheimer's disease. He currently spearheads the Alzheimer's Genome Project, which recently identified 4 new Alzheimer's gene candidates, and this finding has been named one of the top 10 medical breakthroughs of 2008 by Time magazine. Dr. Tanzi has received many awards for his work, including the 2 highest awards of the Alzheimer's Disease Research, the Metropolitan Life Foundation Award, and the Potemkin Prize. Perhaps most importantly, Dr. Tanzi is a Rhode Islander. We're pleased that he's coming back to his home state. He's gone far. He's actually gotten as far as Boston, which is amazing for Rhode Islanders. He's a graduate of Rocky Hill School and Cranston East High School, where he played soccer. He also revealed under pressure during lunch that he's been in a rock group that has played in the Uri area. Maybe if you talk to him at the reception, he will reveal where that was and when that was. He also has the unique distinction of being a rock star of science, which is a special program to promote science and future researchers in young adults. And we're delighted to welcome Dr. Tanzi, so please join me in welcoming Dr. Rudolph Tanzi.
Well, thanks, Phil, for a great introduction, and it's really an honor and a privilege to be here to deliver the Ulyss lecture. Tom Pearls, who was here last year, is a good friend of mine, so I know I'm in good company. And I always love, well, first I want to thank the Rhode Island Geriatric Education Center, the Alzheimer's Association chapter of Rhode Island, and URI for hosting me. And I love coming back to speak in Rhode Island because I don't have to worry about my accent. Because, normally people say, now what kind of accent is that? Is that Boston? Because it sounds kind of like Brooklyn, or so I have to tell them, well, not only is it a Rhode Island accent, but I'm from Cranston, which has its own accent. So, you know, I hope you understand what I'm saying. Also, speaking of Cranston, my mom is here in the audience, Aunt Tanzi, and she made the trip to a great example of healthy aging, right? You don't have to stand up. Now, people tell me when you deliver a public lecture, you know, there are folks who are not biologists and clinicians and scientists in the audience, you should tend to give them to talk to your mother. My mother's here. The problem is, my mother's from the medical field, so if I do that, I'm still going to be a little too sophisticated. No. I apologize in advance if it gets a little too technical, because some of the stuff I present will be a little technical. And there are quite a few scientists and clinicians in the audience, but most of the talk will be at hopefully a regular language level, and my goal is to make everyone understand just how much we know about Alzheimer's disease. And what I'd like to do is, anytime during the talk, if you have a question, just raise your hand, and I'm happy to stop. And I might also ask you partway through if you have questions, because I'd like to make this informal and as informative as possible. So if there are things that if I'm going too fast, or if you have a question, just raise your hand. You know, I think when my band I had back in the 80s used to play at URI, we were always worried about whether enough people would show up. So click on that, enough people showed up. And then we were worried about whether people would dance, you know, because it's bad when you're playing and nobody's on the dance floor. So when you give a scientific talk, you're worried about whether people ask questions. It's kind of like dancing. So we want everybody to dance. So anybody who has questions, please speak up, and we'll also have questions too. So I'm going to tell you a little bit about Alzheimer's disease, and then I'm going to make one major point, and that is that before we found the genes that cause Alzheimer's, we had no idea what caused this disease. We were just guessing. There was an old story about the 5 blind men in the room with an elephant, and they're trying to feel the elephant and tell you what the elephant is, and all they can do is define parts of it. This is how it was since the disease was first described 100 years ago. Describing the symptoms, describing the pathology, no one knew what caused the disease. When we found the first genes between 1987 and 95, then everything changed, because now we had tangible causes of the disease. Just like when we found out that HIV causes AIDS, we started to learn what our villains were in Alzheimer's. And to this day, genetics is still informing us not only on the causes, but how to treat the disease, how to diagnose the disease, hopefully even predict the disease early enough to prevent it before it strikes. And that's going to be the main goal of this lecture, is to basically tell you how we're going to head toward a strategy of early prediction, early detection, pre-symptomatically, and early prevention. Hit this disease before it even takes root in the brain. So for some introduction, Alzheimer's is the most common form of dementia in the elderly. A confirmed diagnosis requires a brain autopsy, but the diagnosis today with cognitive testing is pretty good. Risk factors include age, number one. The prevalence increases dramatically with every decade. Over 85 years old, the prevalence is over 40% based on most epidemiology studies. Family history is the second greatest risk factor. And we know from twin studies that the inheritance of AD there are genetic factors involved in at least 80% of the cases. I think that at the end of the day, it will be tough to find a single Alzheimer's case where there wasn't some genetic influence. But the genetics is very tricky. You have familial cases that usually involve early onset, where you have multiple members of the family showing symptoms, usually by 60 years old. There, the genetics is very strong. But then you have cases where there may be some familial clustering, but they're more or less sporadic cases. Genetics is still involved there, but it may be more subtle, more mild, where you have not causative gene defects that guarantee the disease, but subtle variations in the genome that increase your risk. So when people ask me, well, I have a family member with Alzheimer's who's 75 or 80 years old, yeah, it's probably genetic, but with that later age of onset, the genetics is much more subtle than if you have a family member who got the disease under 60 years old. Life exposure factors for this disease include head trauma, a major risk factor, and stroke. Vascular risk factors, so all the risk factors for heart disease and metabolic disease, obesity, high cholesterol levels are also risk factors for Alzheimer's. Social isolation, so loneliness, not being socially engaged, shown as a major risk factor for Alzheimer's. And I've included this one, insufficient federal funding, because we're still not anywhere near where we have to be at. I'm starting from the Alzheimer's Association here. We need more of this activity. We need more people to write letters, because the funding for Alzheimer's in this country, despite the new presidency, is still pathetic. It's just nowhere near where it needs to be, given the problem this disease is. And I want to show you a little bit about that. Before I do that, just some ways to prevent AD: low-fat diet, anything that helps the heart, reduce cholesterol, physical exercise, probably number one. I would put that as the number one way to stave off the disease based on animal studies. Keep moving, physically exercise. What's good for the heart is good for the brain. Stay socially engaged, take up new activities, always challenge yourself to do new things, and keep on working, whether you're retired or not. Keep working. Mental stimulation is protective. The more nerve connections or synapses you make, the more you can lose before you become cognitively impaired. So these are just some of the ways we know to prevent the disease, but not necessarily guarantee you won't get it. So in terms of prevalence of Alzheimer's, these are numbers from the Alzheimer's Association. 5 million Americans have this disease, but this number will increase to 7.7 million in 2030, 16 million by the middle of the century. And it's estimated that every 72 seconds there's a new diagnosis of Alzheimer's, and by 2050, every 11 seconds there'll be a new diagnosis of this disease in this country. If you look at the breakdown, you can see immediately, starting from 65 to over 85, how the incidence increases dramatically with every decade after 65 years old. And already, Medicare and Medicaid is spending 3 times more on Alzheimer's patients than the average beneficiary. So current costs for Alzheimer's and Medicare and Medicaid are $91 billion per year. This will be up to $189 billion by 2015 if we don't do anything about this disease. So these are pretty scary facts. And this diagram shows here, just looking at the increase in cases, victims, and costs going from 05 to 2030. So you can see this is an epidemic. What you see on the right is federal funding for Alzheimer's disease between 03 and 07. It's going down. Doesn't make sense at all, and this is why we really need to fix things. And this is probably the most scary graph. This is showing you here the numbers of victims of Alzheimer's. This is the Medicare and Medicaid cost here. And you can see here, you probably can't read this, but between 2015 and 2020, the cost of this disease to Medicare and Medicaid will be far outweighed by the number of victims And at this point, we have what's called a tipping point, and Medicare and Medicaid will be crushed if we don't do something about this disease. So we need to let our congressmen and the White House know about this, and we need to have an Alzheimer's federal budget of research well over $1 billion, not at the current 400 or 500 million, preferably even billions of dollars, given the great problem this is, not just medically, but financially. Now, unfortunately, current drugs only treat the symptoms. So when you look at how drugs come about, it usually takes about 40 years from a discovery in the laboratory to getting a drug. So the drugs we have right now are based on discoveries that were made back in the 70s, before we had any idea what caused this disease. Back then, it was noticed that certain neurotransmitters in the brain, neurochemicals that are needed for learning and memory, were being depleted. So the current drugs try to replenish those neurotransmitter levels. So we have drugs like Aricept and Namenda, where you're trying to basically treat the symptoms by increasing the amounts of neurotransmitters like acetylcholine that are used for learning and memory. Well, this treats the symptoms temporarily with some benefit, but it's certainly not a cure for the disease because the disease still goes on. The brain still degenerates, everything's still going wrong. You're just trying to make the most of the neurons and synapses that you have in your brain. Certainly not sufficient, but better than nothing. So I think, and I mentioned this earlier, that the way we're going to really beat this disease is what we would call a personalized medicine approach to AD. This starts with early prediction. We need to know all the genes involved in this disease so that someday we can have a chip so we can tell everyone, here is your overall risk lifetime for Alzheimer's, and then you know up front whether you have to be more concerned or not about this disease. Of course, family history will inform you about that too. And if you are at increased risk, you then need to take into account early detection. We have increasing numbers of ways to see signs of the disease pre-symptomatically, looking at biomarkers in the cerebrospinal fluid, imaging the brain. So if you are at increased risk, you want to keep track of that maybe a little bit more vigilantly. And most importantly, we want to prevent this disease before it strikes. So a great victory that's emerging in medicine today is heart disease, right? So my dad died when I was 17, he was 45, of heart disease. And I take a statin. I don't have heart disease, but I take a statin, like Lipitor, I take Propofol, to keep my cholesterol levels down so that I won't suffer the same fate right away, anyway. Now, we need the same thing for Alzheimer's. We need to know if we're at risk, and we need a statin for Alzheimer's so that we can mitigate risk before this disease strikes. If you have a patient with congestive heart failure, you're not going to do much treating them with a statin because the damage is already done. Same thing with the brain. With Alzheimer's, we need to treat this disease before it strikes. Now, on the other hand, I'll tell you about some drugs that we're developing in my lab and elsewhere that would treat the disease once it already hits. We're going to try to save the brain as well. But we need a cocktail of drugs that will prevent the disease from striking, and also drugs that will treat the brain that's already been affected. And I'll tell you a little bit more of that toward the end. Now, the disease was first described by this fellow here, Dr. Alzheimer, in 1906. And you see this patient, August D. She was a 51-year-old female patient. She was admitted to the asylum in Bavaria, Germany, 1901, with, quote, delirium and frenzied jealousy toward her husband. So back then in Germany, you didn't want to be jealous of your husband because they put you right into the asylum. But anyway, she had severe dementia, and she died a few years later, and Alzheimer's looked at her brain to see if there were any signs of why she became so demented. And at that time, this was considered a pretty outlandish thing to do, because Alzheimer's was considered a psychiatric disease where nothing physically was involved. Okay, psychiatric diseases were not considered physical ailments. So when he came and gave this presentation in this auditorium, and people like Carl Jung were in the audience, and there were little luminaries there, he said, hey, I see these big bundles, we call them miliary foci, these big clumps in her brain, we now call them senile plaques, and I see that her nerve cells are choked, he drew them right here, with these fibrils, and we call those today tangles. He said, I think that this was causing Alzheimer's. And his talk went over like a lead balloon, because no one believed that physical manifestations of the brain could have anything to do with why somebody was demented. And people didn't really believe him. Obviously, he was right. and the disease was named after him by his mentor, Prevalence. But Alzheimer's disease for decades was reserved only for cases of dementia that was pre-senile dementia. In other words, dementia occurring under 60 years old, like an August D. It wasn't until the 70s that this same pathology, plaques and the tangles that he described, seemed to be commonly occurring in those with senility. So when I was growing up, we always heard senility was hardening of the arteries. Okay, we didn't hear about plaques and tangles. But in the 70s, it became apparent that when you look at cases of senile dementia, you see lots of plaques, lots of tangles. You also see loss of nerve cells, loss of synapses, the brain's inflamed, and the brain begins to shrink. You can see these large ventricles here in the Alzheimer's brain. But the real key toward solving the cause of the disease came when we started to biochemically dissect the pathology. This occurred while I was a student at Harvard back in the 80s, and particularly the work of George Glenner, who's now passed on. He was at UCSD, and he basically took the amyloid, not only in the plaque, we call this beta amyloid, in the plaque, and you also see this amyloid, this very sticky material around the blood vessels. This is a cross-section of the blood vessels. And he dissolved it. This was no easy task, because this stuff was really sticky. And he had to use some pretty tricky methods biochemically to get it dissolved. And he figured out what the protein component of the plaque was. What is the protein? And he published this in a very humble, low journal, because people didn't really care about it. And when I was a student at Harvard, I decided that, well, if there's a protein making this stuff up, and George Glenner called it amyloid beta protein, we call it A-beta for short, so I'll refer to this protein as A-beta. So the argument back in the 80s, when I was a student, was, well, proteins are made by genes. You have about 35,000 genes in your genome. They make about 350,000 different proteins. If there's a protein, there's a gene, and maybe the gene that makes that protein is involved in Alzheimer's disease. Now, when I proposed that at Harvard in the neuroscience program, the neurology department, my mentors urged me not to do this. They said, you know, this is just one protein in the amyloid plaque. It's like one tin can in the garbage dump. And it's not going to lead you anywhere. And luckily, I played in a rock band, so I couldn't hear so well. So I didn't listen to any of them. And that turned out well, because as it turned out, the gene that makes the amyloid beta protein, I mean the amyloid precursor protein, APP, in 1987, and this turned out to be the first Alzheimer's disease gene. What we learned very quickly in 1987 was that if you look at this little yellow segment here, that's the A-beta. It's embedded in a larger protein shown here. So this is the surface of the nerve cell. This is outside the nerve cell. Here's the outside part of the protein. Then it goes through the surface of the nerve cell membrane, and then here's a little bit inside. This yellow piece is the amyloid beta protein. So to release it, you have to have two clips, two enzymatic scissors. One is called beta secretase, which cleaves here. The other is called gamma secretase, which cleaves here. So you get clip, clip, the little yellow piece is released, and if you release enough of it, it starts to clump up, and now you start to form an amyloid plaque. So overnight, we suddenly understood where the beta amyloid was coming from, and it was coming from this protein. It was made by a gene that, lo and behold, we now know contains 29 different mutations that can cause the early onset familial Alzheimer's disease, where the onset's usually around 55 years old. These mutations are really bad. They guarantee onset of the disease. Luckily, they're very rare. And then we found after that these two genes, we discovered these in 1995, presenilin-1 and presenilin-2, where you have 169 gene mutations here, 11 here, all of them causing, again, early onset familial Alzheimer's. This particular gene makes these scissors. So, you know, slap us in the face a few times and get it. You have APP, and here are the scissors that make the second cut that release the amyloid, and the gene that makes the APP and the gene that makes these scissors both can contain mutations that guarantee the disease, early onset familial Alzheimer's, under 60 years old. And again, luckily these mutations are rare. They're less than 1% of the disease, because there's no escaping Alzheimer's or inherited. although they're rare, because their biological effect is so strong, they've taught us more about this disease than anything else we've learned about Alzheimer's so far. And as you might imagine, the drug industry is now targeting those enzymes, including the presenilin-based enzyme, for drug discovery. And I should add that most of the mutations in early onset disease are in presenilin 1. That's this big protein shown here that clips the APP. There are 364 families worldwide described for this, and the average age of onset there is 44 years old. We have a presenilin 1 mutation family. The onset of the disease is in the early 20s. They have Alzheimer's in the early 20s, symptoms start in the late teens, and they have full-blown Alzheimer's upon autopsy at 25 years old. So these are really bad mutations, but again, these really hard-hitting mutations teach us the most about what's going wrong because you have a real given in the equation as far as something that's defective. Now, when you study these mutations, we learned something that was pretty clear-cut, and that's shown down the bottom. Most of these mutations, not all, but most of them, increase something called the ratio A-beta 42 to A-beta 40. So think of cholesterol, right? You have good cholesterol and bad cholesterol. Now, I'm not going to say there's a good A-beta and a bad A-beta, but there's a bad A-beta and a worse A-beta, okay? A-beta 42 forms the plaques much more readily than A-beta 40. And usually in your brain, about 90% of the A-beta is the 40 type, 10% is the 42 type. When you inherit these mutations, most of these mutations increase that ratio. So you get a little bit more 42 versus 40. And that 42 is much more prone to driving the amyloid formation. And what we learned after, well, brings us right up to about 1999 at this point. So we spanned already about 99 years. What we learned is that if you increase that ratio of 42 to 40, just like increasing bad cholesterol to good cholesterol, you're prone to higher risk for Alzheimer's. Why? Because that ratio increases the rate at which the A-beta proteins aggregate into clumps that eventually turn into plaques. So that's the main message so far. I wanted to stop and ask if there's any questions so far. Yeah.
What tips the ratio that you get more 42 a certain stage?
So what tips the ratio? So the presenilin 1 is part of the second enzyme that clips over here in the membrane. And when you have mutations either in APP, around this spot in APP, or in the enzyme, presenilin gamma secretase or presenilin that clips it, instead of clipping here, you clip 2 amino acids over. So instead of making 40, you skip 2 amino acids in the protein, clip 2 down, and that gives you 42. And it all has to do with how these things sit in the membrane. They dock in correctly with each other. When you clip, you make the extra long A-beta, and that's just much more prone to forming a lot more of these clumps.
I understand how A-beta 42 is formed, but as you age longer, 42 increases over the 40s. What happens to lead to that production of more 42 over 40?
Yeah, so the question is, what we don't really know is, does the 42 to 40 ratio increase with age?
And you have to deal with it.
Yeah, I mean, the early onset cases show us that 42 to 40 does this, but as we increase with age, some people like Steve Young can say the 42 to 40 ratio increases. We don't know how. We really don't. But it's still not full agreement about whether that's a generalized phenomenon in Alzheimer's disease. And even if it were, we don't know how it happens. It's a great question. Yep?
We have a brother-in-law who has early onset Alzheimer's at the age of 56. And I noticed the statistics you had there was only 1% of people who get early onset. I thought it was 10%.
So there's a lot of confusion, especially when you read about it in the media. 10%, you can see clear familial inheritance as defined by the patient having 2 or more first-degree relatives with the disease. But some of those familial cases are over 60 years old. But we use a cutoff of 60 for early onset. Now, what we know is about 2% of Alzheimer's occurs under 60. And those 3 genes I showed you here only account for half of the early onset. There's still half of them missing. We don't know what they are. So when you do the math, this is about 1% of the early onset. Well, 1% of AD and about half of early onset of AD.
Also, we never had any gene work done, and they never asked to do it. Is that standard for them not to ask? They only did it when there was a drug trial, and they tested it to see if you had the safety of over 14. And then they wouldn't tell you the answer to the question when she did the study.
Well, generally, if onset in a family is under 60, and there's a chance for one of these mutations, the option for genetic testing is there. It becomes a very personal decision. It's done with genetic counseling, also psychological counseling. It is available, for example, Mass General where I am and other sites. So it is available to you, but it's a very personal decision as to what you want to know, given that we can't empower you yet with the therapy. But it is out there. Yeah?
You say brain autopsy is the only way to certainly diagnose this, but what are we seeing on our brain imaging techniques at this point?
Yeah. So at this point, you know, cognitive testing, psychological testing is pretty much 90% accurate. If you look at diagnosis versus autopsy, at most, you know, institutions that are really doing this a lot, it's approaching 90% accuracy rate. Imaging on top of that can increase the accuracy rate over 90%. So imaging is used as an adjunct diagnostic over cognitive testing, but is not sufficient in itself to tell you with certainty whether there's Alzheimer's disease. Although there are some brain imagers, for example, on the West Coast, who will claim that they can do it with certainty, but that's not generally dominant in the field yet. Yeah?
If we check the blood of healthy people, do they have deviation of 42 and 40 and 41?
So healthy people have tons, I'll tell you later on that A beta is actually not just junk, it actually plays a role in the brain EEG. And about 90% of the A beta in the brain is 40, A beta 40, so it's 40 amino acids long, and about 10% is A beta 42. But if that ratio increases, then you get into trouble. But there are other ways to get A beta to accumulate without the ratio, just having more A beta, for example.
Are they any critical concentration that we have?
I can't, will they say it again? Sorry.
If we check the concentration of A beta 40,
Yeah.
about which concentration that we should do that first on the start?
Yeah, the problem is that you can't measure these concentrations because they're in the brain. And so you can do imaging for amyloid in the brain where you can see the plaques and some of the bigger deposits using something called the Pittsburgh compound. But we can't, it would be great if we could measure A beta levels in the brain the way we measure cholesterol. But we can't do that. And if you try measuring this cerebrospinal fluid, it gets tricky because as you form plaques, instead of the A beta coming out of the brain, it gets stuck on the plaques. So it's almost impossible to know how much A beta you have in your brain while you're still alive. We wish we could know that. That would be great.
Is it possible to check the blood for that?
No, the blood, you can see A beta in the blood, but it's not a reliable reflection of how much A beta you have in your brain. Folks have tried that for a couple of decades now. It's just not reliable. And again, it's because the A beta in the brain may not get out of the brain because it gets stuck on plaques. The plaque is like Velcro. So if you just measure what gets out, it might not tell you how much is there because it gets stuck inside. Okay, let me move on then. I just told you about the rare early onset cases, but we also know is that there's a late onset, more common Alzheimer's disease risk factor called ApoE, or apolipoprotein E. This gene is usually involved with cholesterol metabolism. And there are basically 3 different versions of it. Most of us have E3. There's a rare form called E2, and then there's a form called E4. And E4 is in 20% of the population, so 1 in 5 people in this room carry E4. When you carry 1 copy of E4, it increases your risk for Alzheimer's over 3-fold. And if you carry 2 copies of E4, 1 from mom and 1 from dad, it increases your risk over 10-fold. But importantly, E4 does not guarantee you'll get the disease. So this is different than the early onset mutations. The early onset mutations guarantee the disease. E4 increases your risk. And even though this was discovered back in the early 90s, we still don't know exactly how ApoE does this. We don't know exactly what's so bad about ApoE4. But it is certainly the most well-established late onset risk factor or variant in our genome. So when you think about the human genome, there are rare mutations like the early onset gene mutations, and then there are common variants like E4. In this case, the common variant increases risk but doesn't guarantee the disease. What we do know is when you carry an ApoE4 that you're more prone to having greater aggregation of A beta in your brain. It doesn't get cleared out as well. So it's thought that ApoE plays a role in clearance and aggregation of A beta in the brain. So this is what we've learned so far. If you look at the 4 known Alzheimer's genes that we've had for about a decade or so now, the 3 early onset genes affect how you produce A-beta, and the ApoE late onset gene affects the rate at which you clear it from the brain versus having it aggregate. And if you have too much A-beta accumulating in the brain, this then seems to drive Alzheimer's pathology. Now there's been some controversy about this because if you count the number of senile plaques in the brain, senile plaques in the A-beta overlay, if you count the numbers of plaques, it doesn't necessarily correlate with the degree of dementia in a patient. So there have been those who say you're chasing the wrong thing with the amyloid because the plaques don't correlate. What I'm telling you today is that most of us don't believe the plaques are the problem. The plaques are the end game. They're telling you that what happened. It's like going to a football game after it's over and seeing all the junk in the stands and on the field and trying to figure out what the game was. That's what a plaque is. You have to think what really happened getting to the plaque. And what happened getting to the plaque is that the little A-beta pieces sticking together, 2 of them stuck together here, 3 stuck together here, these little pieces get into the synapses where neurons are communicating and cause short circuits. So if you think about your brain as a neural network, a neuronal grid, and you have all this incredible amount of communication between nerve cells, little bits of A-beta, way before it's in the plaque, is going to short circuit the synaptic communication, the actual neurotransmission that forms your neural network. We think this is the problem. So the plaques are way down the line. And the genes we know about will all increase the amount of these little, here 2 stuck together called a dimer, 3 stuck together, a trimer. These are generally called oligomers. That's probably the most complicated word I'm going to use today, oligomer. I don't know what word. But here, it's shown here. Here's a single A-beta, 2 stick together, you get a dimer. 4 stick together, you get a tetramer. 6, a hexamer. And then the hexamers start to stack, like you picture like bolts stacking on top of each other. And eventually this becomes, if you picture like 1,000 of these stacked together, eventually you get a big long 5-one. And that big long 5-one is what you get into the plaque. But the problem is caused by these guys. And this is what A-beta 42 does. A-beta 40 does this. You get 1, 2, and then 4, and it stops. With A-beta 42, you get these hexamers, and they start to stack, and these are probably the most toxic. So that's why 42 is worse than 40. So once you start getting these guys, they get, like I said, they start causing synaptic dysfunction, and then the nerve endings start to prune back, and this is when all the trouble begins. Eventually, you'll also get inflammation as plaques start to form, and this is all downstream of these original results. But this is how we believe, from the genetics, the disease is being caused, is you have to target these guys early in the game, before you get too many of them in the brain. Yep. The zinc and copper, and I'll get into this, it's a great question, because what we discovered in my lab in the early 90s is that in order for a single A-beta to form these toxic entities, you have to have copper and zinc. Copper and zinc drives this reaction. And so we actually are developing a drug that's doing really well right now that prevents the zinc and copper from interacting with the A-beta, and we can prevent or at least turn down the amount of oligomer that forms. And this is how we're trying to neutralize the toxicity of the amyloid. And this is actually going very well with the company that we started in my lab, and now it's in Australia. Yeah.
So the people using copper utensils are more prone to Alzheimer's disease?
I didn't hear, I'm sorry.
People who use copper utensils.
Yeah. We don't worry about copper utensils. It's the same thing with aluminum. You know, in this case, the amount of copper in your brain stays pretty much constant. It's just how much of the copper is available for interaction. So you don't really have to worry about copper levels. I mean, unless I guess extreme cases of like a guy who had copper pipes and there was an electrical wire going into the water and it's causing the copper to leach out into the water. So he was actually getting full-blown copper toxicity and dementia. But for the most part, you don't have to worry about copper utensils because these metals stay pretty much to themselves in the brain, pretty much regulated. Yeah.
I'm trying to write all this down. Is this available online?
I think so. This is being cast on the web.
Yes.
It's going to be on YouTube, and I think it's a simulcast of this. So yeah. So you can just write. You can just read this. Yeah. Well, you know, I hope that the Elon, Wyatt, now J&J collaboration works, and they're using antibodies to target the amyloid. And it's stimulating the breakdown of the plaque. One study that just came out from that trial, there's a small number of patients, but they were able to actually remove plaque to a certain level with the antibody treatment, the immunotherapy. But when they used the Pittsburgh compound to image the amyloid in the brain, they saw there was a reduction. But there was no cognitive improvement in those patients. So it could be the sample's too small and we have to wait. That's the optimistic view. The pessimistic view is that the plaque's not the target. You can remove all the plaque you want, you may not be removing these little guys. And we don't know for sure whether that immunotherapy is removing plaque plus these little guys. In my opinion is if you don't remove these guys, you're still going to get cognitive problems and breakdown of synapses in neurons. So jury's out, and it depends if you're optimistic or pessimistic about the trial.
So you say that the copper and the zinc are important for making these polymers of the data. So,
Yeah.
So the metal chelators are one of the therapeutics.
Yeah, the metal chelators are too harsh. We don't believe in chelation therapy because you don't want to remove metals from your body. You need them, right? The drug we're using, I was going to get to this at the end, so I'll just say a little bit right now. The drug we're using just interferes with the interaction of A beta with the metals, but it does not remove the metals from the system. So you don't want to use chelators because they're too harsh. And I have a whole couple of slides on that. Okay, so the main problem, as I just told you, is that the A beta is accumulating, and most of the problem, you know, among your 100 billion neurons, you know, 100 trillion synapses in your brain, is the A beta, like I just said, is forming these little oligomers, and where you're trying to have one neuron contact another right here, you're going to cause a short circuit, and eventually these nerve endings prune back and start to degrade, and then at some point later you're going to see a plaque in that area. And the plaque is going to have the middle core of amyloid with all these dying nerve endings around it, but it starts like this. So this is the target. We need to hit this stuff. We need to try to turn down the amount of oligomer in the brain. Now before I get to the last part of the talk, which will be how do we do that? How do we treat this disease? How do we cure it? And I'm going to let you guys do that for me. Let me just tell you an important fact. In our Alzheimer's Genome Project, why are we still doing this? And it's because all these 4 genes that have driven everything basically we know about this disease biologically account for less than 50% of Alzheimer's genetics. In fact, one estimate says that these 4 genes only give 30% of the story. So I've argued that, well, if we've learned this much from these 4 genes, imagine if we had the other 50 to 70% of the story, how far we could go. So as we started this Alzheimer's Genome Project, where we used this whole genome screening using these gene chips, like one shown here, and this is the machinery we have in our lab to do it. And we're screening the entire human genome. And what we're using is variations in the genome. So you know that your DNA is 3 billion bases. So it's like the double helix, and you have 3 billion bases of DNA. Well, it turns out that between any 2 people, there are about 3 million differences. So every 1,000 bases on that 3 billion base string, if you put all your chromosomes end to end, every 1,000 bases is a difference between you and the person next to you. And so between any 2 people, there are 3 million bases of DNA that are different. And if you look at all of humankind across the planet, there are 30 million differences in the DNA across all of humans. Now, some of these will be called single nucleotide polymorphisms. That's just a fancy way of saying a difference in the DNA, one base difference. We call it a SNP, SNP or a SNP. And most of these SNPs are just neutral. They don't mean anything. But some of these SNPs can actually cause the disease. Like those mutations I showed you in APP and apresenilins that cause early onset AD, they're SNPs, but they cause the disease with certainty by 50 years old. Some SNPs, like the ones in ApoE, increase your risk. Some SNPs just modify the course of the disease. But we use these SNPs as markers in the genome to track where the disease genes are. We follow the inheritance of 1 million SNPs at a time, covering the entire human genome, using those chips. And in this way, we can identify blocks of the genome that are being co-inherited with Alzheimer's in families. And by doing that, we can go to that block in the genome and say, what gene is there? And say, here, we have a candidate for a new Alzheimer's gene. It's incredible technology. This all started back in 1983, and I was very lucky then to work with Jim Gasella, and we were the first, we found the first 12 SNPs in the human genome back then, and actually at that time I was still playing in a rock band here in South Kingston as well. I was commuting over to Boston, and it took us 3 years to test the first 12 SNPs in 200 samples of families with Huntington's disease. So it took 3 years to generate 2,400 genotypes. In other words, to test 12 SNPs in 200 patients. It took 3 years. And in this way, we were able, for the first time ever, this was the first time a genetic marker, a SNP, was used to find a disease gene. And this really launched the Human Genome Project. It was Jim Gasella's idea, and I was basically the hands that did it in the lab. But it was a very exciting time. Now you fast forward 25 years or so. Now, in 6 months, in my lab, we can test 1 million SNPs covering the whole genome using these chips in 1,500 samples. So we can generate 3 billion genotypes per year. So we basically have increased our productivity by 1 million-fold. Pretty amazing. So this allows us now to scan the genome to find these other disease genes. And this just shows basically, which you heard earlier from Phil Clark, that we found 4 new candidate genes that we're now looking into, but we also have about 70 other genes that we're also looking at, all as candidates for Alzheimer's genes. One of them we found was a big surprise. Caption 1 is the gene that causes a movement disorder known as spinocerebellar ataxia. What we found was that the same gene that can cause spinocerebellar ataxia, where a part of the brain's spinal cord starts to degenerate, different mutations in this gene can instead lead to Alzheimer's disease. So this was a big surprise, and we're very actively studying this gene in Alzheimer's now. Sure enough, mice, when you knock this gene out of their genome, become cognitively impaired with the same symptoms as Alzheimer's disease by 6 months old. And now we've also learned that this gene regulates how much amyloid beta protein you make. So this just shows how powerful the unbiased approach is. We scanned the whole genome. We didn't have any preconceived notions about which genes would be involved. Look at the whole genome and see what falls out. I would have never predicted this is an Alzheimer's gene, but that's the power of unbiased screening. So this gene falls out, and now we find a whole new gene and protein in capsin 1 that is also regulating A beta production. This could become another target for drug discovery, so you can see why we do this. Another gene we found is called ADAM10. What I didn't mention earlier is that, you have, here's APP that makes the A beta, here's a little A beta piece in here. So I said in order to excise, you have to have a clip here and a clip there. Well, normally the APP gets clipped right in the middle of A beta. So normally this clip is made by alpha secretase, and you cut the A beta into 2 pieces so you don't make amyloid. We found most recently that the main gene that makes the alpha secretase, ADAM10, we found 2 mutations in late onset cases. Again, this came out of the genome-wide screen. So we're starting to find not only new candidate genes, but we're also starting to find mutations that can lead to Alzheimer's in the more common late onset form as well. We keep all of this information for those of you who want to follow up. There's a website called alzgene.org that we maintain. Every Alzheimer's genetic study ever published is curated, and on this website, 660 different genes, 2,800 different SNPs, 1,355 different studies, and for any of these variants that have been tested in multiple samples around the world, we do what's called a meta-analysis to see which of them which are strongest. So if we went to the website today, you would see this list of genes. There are 38 different genes, rank ordered by how much they affect the disease risk. And this list is changing as new publications come out. So it's kind of like watching CNN or ESPN Sports Center. Things change with new results. So if you went to this site and you wanted to keep track of what looked like real Alzheimer's genes from all these different genome-wide screens, you can go to this website and see this list. And then you'll see ApoE is number 1 for late onset AD, and then they're rank ordered down to the bottom. And this gets curated and reviewed every 2 weeks. So for the aficionados out there, you can check the gene list yourself. And then if you have any ideas about how to cure the disease from this, please email me and we'll give it a shot. So let's get to the last part of the talk. With all these genes, what have we learned about treating this disease? Now, here is a killer graphic. And I'm going to walk you through it because we're going to use this graphic to cure the disease. Here's APP. Like I said, you have to click here and here to release the A beta. If you make too much A beta 42, the long form versus the short form, you drive the aggregation of A beta. You need copper and zinc for this process. These little guys, 2 A beta stuck together, or 3, or oligomers, get into the synapse. They prevent neurotransmission. Of course, without proper neurotransmission, cognition starts to get impaired. Eventually, these form into large fibrils and you get a plaque. Along the way in this process, you get inflammation in the brain. Inside the neurons, you start to form these tangles as the neurons get sick, and eventually the neurons, nerve cells, start to die. On the other hand, A beta you can have alpha secretase of APP, and that precludes the formation of A beta. Or even if you make A beta, much of it can be cleared from the brain with the help of ApoE, and it crosses the blood-brain barrier and goes into the blood, and it can either be degraded in the brain or the blood. So this is what we've learned from the 4 known genes. And then, with all of these new studies we're doing, all of these genes can be added. You can see how all these new genes we're finding from these genome-wide screens are fitting nicely into these boxes. Some are involved with inflammation, some involved with the synapse, or the formation of the fibrils, some affecting aggregation, some affecting clearance, a whole lot of them affecting how you produce A beta. So we're starting to fill in this diagram as we find more genes. And importantly, every new gene we find not only increases the reliability with which we can someday predict risk for the disease, but each new gene presents a new potential drug target. So the gene can teach you what type of drug you need to prevent some process here to treat the disease. So I want you to tell me, how do we treat the disease? What do we do? We know that you produce A beta, you have 42 over 40, it aggregates, it appears to synapses. Any ideas about, based on this information, you're running a drug company. What do you want to do? How do you treat the disease? And don't be shy. Put some dances on the dance floor. Mom, come on, you can say something.
Get rid of the zinc.
Say again?
Work on getting rid of the zinc.
Work on getting rid of the zinc. Thank you, my favorite one. So what you can do is basically, if you prevent the copper and zinc from interacting with the A beta, you will prevent these oligomers from forming. You basically neutralize the toxicity. And I'm going to show you a slide in a moment of a drug where we're doing that, and we're getting great results in clinical trials. Other ideas? How about up here? Anything we can do up here? Say again? Reducing the cutting. Yeah. So if you want to get way up here, you can target drugs against the beta and gamma secretase that release the A beta from APP. And drug companies are doing that, but it's tricky because these enzymes that make these cuts are also needed for other reasons in the brain. So you can't just hit them with a sledgehammer. You have to hit them very carefully in a way that's selective for APP. And actually, my colleague Steve Wagner and I started a company called Neurogenetic Pharmaceuticals. We have a class of drugs that we call gamma secretase modulators, or GSMs. You'll hear more about these, I'm sure. That very selectively knock down those cuts, but safely, so that it only hits APP, you don't cause other side effects. And those drugs are currently not in the clinical trials yet, but we're hopefully going to get into a safety trial with our first drugs next year. And we heard your suggestion here, block the aggregation into these oligomers with the zinc copper drug, so prevent the zinc copper from interacting. Any other ideas as we work our way down the diagram? Yeah. Yeah, you can try to prevent the inflammation down here. Now the problem has been, and the trial was done with ibuprofen, and the trial was also previously being done with COX-2 inhibitors before they had all those problems with Celebrex and Vioxx. The problem is, it may be too late. So if you wait for the inflammation to occur, by that time the brain might be too sick. And so the ibuprofen results were not very positive. But otherwise, it was a great idea. There were clinical trials that just done.
Didn't you have on one of those slides an APOE that was somewhat protective?
Yeah.
Would that increase that somehow?
Yeah, so that's good. So that's number 3. You try to increase the clearance of A beta from the brain, or enhance its degradation, where ApoE plays a role. And the way that's being done right now, we heard a question earlier about the immunotherapy from Elon, Wyatt, J&J. So we have antibodies that come in and try to promote the removal of A-beta from the brain or promote its degradation. Now, as I mentioned before, it's tricky because these antibodies can also cause some side effects like edema around blood vessels and microhemorrhage. So the question is, will they get just the right dose so that it's safe? And are they going to hit the right A-beta? If they hit the plaques, that might not be enough. You have to hit these oligomers as well. So we just have to see how the trial goes there. And I'll just finish it off here. You can also try to prevent the tangles from forming here. You can try to protect the neurons from dying. This is all pretty big stuff. And currently our drugs just do this. They let all of this go wrong, and they just treat the symptoms. So you can see that that's why we need so much more research. We need to be treating up here, nipping the disease in the bud stage, not treating down here. Yeah.
Not to plug our research, but we have a provisional patent for a drug at URI where it does upstream there. It stops the production of APT messenger RNA and the APT protein. And then you see the A-beta go down with it.
Right, so the suggestion here with a drug that's on the provisional patent here at URI is that we try to prevent the production of A-beta by lowering the levels of APP at the level at which the gene makes the protein. So the gene makes the protein by what's called transcription of the RNA, and there's a drug here that lowers that transcription, and by making less APP, you make less A-beta. That would be particularly useful for Down syndrome, because Down syndrome kids have 3 copies of APP. They have more than they need. So if you could turn down the production of APP, that drug, that would be beautiful.
That's one of the things you want.
Yeah, to be careful. So these are the 6 ways you can do it, and I thank you all for helping me with that. I mentioned that the drug I'm really excited about is the one that prevents the interaction of copper and zinc with A-beta, preventing it from forming the oligomers that appear to synapses. This drug is called PBT2. It's from a company called Prana, P-R-A-N-A. It's a company that started in my lab back in the 90s and then moved to Australia because our angel investor who gave us the money for this was from Australia, and the company's now going public there. And very exciting, this is a paper coming out in 4 days, is that our phase 2A clinical trial for efficacy, we were the first drug that have been able to, in targeting the amyloid, significantly increase what's called executive function. So when you look at cognition, there's the memory aspect, which we didn't have much effect on. Then there's executive function, which is more like parallel processing, keeping multiple tasks going, cooking dinner, answering the doorbell, remembering dinner's being cooked. Many neurologists I talked to say if they had a choice, you can have a pill that either cures executive function or working memory, they'll take executive function because that's how you improve everyday living, keep someone out of nursing home. So we had very promising effects on executive function in this small trial, and now we're gearing up to do a larger trial with 500 patients over 1 year. This was just 78 patients in 12 weeks, and we got effects. So we're very excited about this. And again, the mechanism is very simple. We're preventing zinc and copper from interacting with A-beta, but we're not chelating it. Okay? The copper and zinc, after it's prevented from interacting, actually becomes available for use in the brain by other enzymes that need it. So it's actually the opposite of chelation. Do you have a question?
What are the what's the people you're using for the setting? People with MCI or Alzheimer's disease?
So basically this is an MCI under 25. I'm sorry, MMSE under 25. So we have the moderate patients between under 20. And we have a mild set between 20 and 25. There were 78 patients. Most of them were APOE4s. It was equally split between women and men. That was the 78. We're going to do the same thing with the 500 people in the phase 2B with the larger trial. But basically 15 to 25. So just one last comment. You know, this drug and many of the drugs we just came up with in the audience are targeting the A-beta. We're treating this stuff as if it's junk. And I just want to give a little bit of caution here. This is a recent paper we just published over the last month where we found that A-beta may actually have a role in the brain. So you don't want to hit it too hard. What we found, and I'll just summarize this quickly because it's getting late, is that A-beta is part of the brain's innate immune system. It turns out the brain is immunoprivileged, right? So the brain doesn't use antibodies and all the sophisticated immune machinery we have in the body. The brain is ancient immune system, same thing that a horseshoe crab uses, okay? instead of making antibodies, it makes something called antimicrobial peptides. Small little proteins or peptides, like A beta, that kill bacteria, viruses, fungus, even cancerous cells as they appear in the brain. This is exactly how an oyster, lower organisms protect themselves. The brain is old school when it comes to the immune system. And what we found is that A beta is one of these antimicrobial peptides. It actually has as much or more activity against a whole host of antigens, a whole host of organisms. Candida albicans, the yeast, Staph epidermis, Listeria, Staph aureus, leafy salus. It hits all, Staph pneumoniae. And A beta is now added to the list in the innate immune system. The innate immune system is your first defense. Before antibodies come along in B cells and T cells, your body wouldn't be living if you didn't have your innate immune system, where there's an immediate attack against bacteria with antimicrobial peptides. Turns out A beta is one of these in the brain. So I'm warning drug companies now, don't hit A beta with a sledgehammer. Show a little respect because you need something. So I'm suggesting that you treat it like we treat cholesterol. We don't completely turn off cholesterol to prevent heart disease. We use a statin to dial it down to a safe level. It'd be great if someone asked a question, can you measure A beta in the brain? Well, we can't. But if you know your risk factors genetically, if we get some idea about prediction about your accumulation of amyloid based on your genetics, we can put you on a statin equivalent of A beta. Same way we bring cholesterol level down safely with statins, if we can bring A beta levels down safely but not turn it off, because I think you need it, then we'll be able to prevent this disease early in life. So this brings me then to this just shows two bacteria here being attacked by amyloid. And this brings me to my last slide about how I think Alzheimer's is being caused, given all this information. Now I'll just go to this slide here. What will happen is that as we age, as the brain undergoes insults, stroke, traumatic brain injury, mini strokes, neurotoxins, unnoticed infections that are fought off by the brain, because A beta is part of the innate immune system, all these little insults over time, over the lifespan, are turning on the innate immune response in the brain, and this turns on the production of A beta. So now A beta is starting to accumulate as a normal thing in the brain. But if the A beta accumulates too much, the A beta itself becomes neurotoxic. Too much of a good thing is bad. So now you get too much A beta because you have too many of these insults. Too much A beta accumulates, and now the A beta becomes the insult and starts this whole cycle going again, so you can get a vicious cycle going. And what we're finding in our genome-wide screens is that the genetic factors are very neatly fitting into all these boxes. We have a whole bunch of genes that affect the innate immune response, a bunch that affect A beta aggregation and production, some affect your predisposition to stroke, for example, the insult, some affect clearance of A beta, some affect inflammation. So this whole vicious cycle is being regulated by your genetics. So knowing this, what we hope to do someday is a true personalized medicine approach to this disease. Find all the different genes, predict your risk early in life. This must be done with proper genetic counseling, psychological counseling, and very importantly, genetic privacy laws. You don't want to have your genetic risk determined if your insurance companies can use it against you. Right now, regarding genetic privacy, there's an act that was passed, a bill that was passed called GINA, the Genetic Information Non-Discrimination Act. It protects you and your genetic information from discrimination by health insurance and by employers. It does not protect you against life insurance or long-term care. So I'm working right now with some folks in Washington for GINA 2 to get that out, because if you're going to do this someday, you need complete protection, but you cannot be discriminated against by your own genetic composition. So let's say we can do safe, safeguarded, reliable genetic testing. Now you know your risk. In addition, you know your family history. If you're at increased risk, there are ways, for example, using imaging we heard about before, biomarkers, so that you can start to detect early signs of Alzheimer's before cognitive symptoms show up. And then the hope is that with all this information we're learning from the genes, with these new drugs that are being developed, that we just went over, that we can prevent this disease from striking in the first place before the disease strikes. Same way we're treating heart disease. So this is the goal, but it's all being driven by the genetic information from diagnosis, prediction, and then hopefully early prevention. And that's going to be the goal going forward over the next decade. These are really the pioneering days, but I think it's all very exciting, and remain very hopeful and optimistic about the future. So I'm going to basically just wrap up. I do want to acknowledge my lab. This is just a summary of what I just told you. That I want to say that, but I think by the middle of this century, by 2050, we'll no longer wait around for life-threatening illnesses to strike. I think that 2050 or so, they'll look back at us and say, boy, those poor people at the turn of the century, they had no idea what diseases they were going to get. They didn't know what they were at risk for. They just lived in this blind, blindness about what they might be at risk for. They didn't even try to prevent diseases before they struck. I think it's going to seem pretty archaic of how we're, by 2050 or by the end of the century, when preventative medicine will evolve this mantra of early prediction, early detection, and early prevention. And I think Alzheimer's is really paving the way for not just Alzheimer's, but also cancer, heart disease, stroke, diabetes. All of these diseases that threaten healthy aging can be beat this way by knowing up front your risk, detecting early warning signs, and preventing disease before it strikes. And the genes, in all of these cases, the genes are teaching us how to do this. And this is what we're involved with right now in Alzheimer's. And I hope you got a bit of that from this lecture. And I just want to acknowledge all the folks in my lab who do this work, particularly Christina Mullen, my lab manager, who's a URI alum, and all my collaborators around the world. And I want to thank the Cure Alzheimer's Fund in particular for their funding of the Alzheimer's Genome Project. Thank you very much for your attention.